Okay, this will be part 3 of the second derivative and concavity series. And if you have not done it yet, I would definitely watch the first 2 parts because they will show you where this series of 6 steps come from that we'll be using in this video. Now, in the part 2 video, we found intervals where a function was concave up or concave down, but the example problem we used there was a polynomial that didn't involve asymptotes. So the difference between the previous video and this video is that this time we'll look at a rational function that will have asymptotes, and it changes just a little bit how you have to go about this. So here are the steps that we used before. Now again, I'm assuming here that you have just watched the part 2, so you understand where these steps come from, so I won't run through them again. If you haven't done that yet, I would go back and watch that one before you start watching this. So we're going to run through these steps. Now the idea was this, is to find intervals where the function is concave up or concave down, you needed the second derivative and inflection points, because at an inflection point, the graph could change from concave up to concave down. So the idea is find the second derivative, set it equal to 0, solve for x, that gave you the inflection points, divide the graph up into intervals, pick a convenient test point inside each interval and test the second derivative. If the second derivative was positive, it's concave up in that interval. If the second derivative is negative, it's concave down in that interval. Now, in that previous example, we didn't use this step 3b here. Find any values of x where the second derivative was undefined, because polynomials are defined everywhere, so this wasn't a problem. But what you'll find when you're working with rational functions is that wherever the original function has an asymptote, all the derivatives are undefined at that point. So this time, the second derivative will be undefined at an asymptote, so we'll have to consider that. But otherwise, we'll run through the same 6 series of steps that we have right here. Okay, so with that in mind, let's take a look at the first example. Okay, now here's the rational function. F of x is equal to negative 2x, and you've got an x squared minus 1. Now, if you just follow the steps that we have, let's go ahead and put those right back up here again. Step 1 would be to do the following. Step 1 would be go ahead and find the first derivative. But what we'll do, whenever you work with a problem that involves asymptotes, I would suggest that you, first of all, consider the asymptotes, because the asymptotes could behave as an inflection point. Now again, strictly speaking, an asymptote is not an inflection point, because an inflection point has to be a point that actually exists on the original graph. And since the original graph is undefined at the asymptotes, then an asymptote really can't be an inflection point, but it can behave as if it's an inflection point. So the first step on this process will be the following. We'll go ahead and find the asymptotes. So my initial step whenever I'm working with a rational function is to find the asymptotes. So we'll put that as our first step. So find the asymptotes. Now the asymptotes occur wherever the original function is undefined, and that's going to occur where the denominator is equal to 0. So take the denominator and set it equal to 0. So x squared minus 1 is equal to 0. And that gets you to x squared is equal to 1. Take the square root of both sides and you'd get x is equal to plus or minus 1, which means x is equal to a negative 1 or x is equal to a positive 1. And what these are your asymptotes. So you're going to have an asymptote at negative 1, and you'll have another asymptote at positive 1. So those are the asymptotes. Now, just like in the previous problems, you don't have to sketch a graph, but I think all these things make a lot more sense if you do take the time to sketch a graph. So what I'm going to do is go here and put these points on the graph. So what I'll have here is a negative 1. I'll go ahead and put that about right here. Now what I've got here is an asymptote. So I'm going to go ahead and put a dotted line to represent the asymptote right through negative 1. Then I've got another asymptote at positive 1, so I'll put that over here. This is going to be a positive 1, and I'll put an asymptote right here. So I've got an asymptote that goes through there. So again, just a quick sketch of the graph. So what that is this was an asymptote here, and you've got another asymptote over here. So that will help us divide this thing up into intervals to find out what's going on in each interval. Okay, now that we've got the asymptotes taken care of, now we'll go back and run through the steps in this solution. So let's take a look at the steps. So the first step says to get to the second derivative, you're going to need the first derivative. So the very first step is go ahead and find the first derivative. Now this becomes a little trickier in this one because in the last video you did not have to use the quotient rule. But in this one you're actually going to have to use the quotient rule to find that. So we'll go ahead and put that under. So step number 1, you want to find f prime. So you want to find the first derivative. But to do that, you have to use the quotient rule. So let's go ahead and run through this. So the quotient rule says that it's the denominator times the derivative of the numerator. So the derivative of the numerator would be minus 2. Then minus the numerator, the original numerator, times the derivative of the denominator, which would be 2x, and then the whole thing divided by the denominator squared. So it's this entire thing divided by the denominator squared. Now, you can go ahead and simplify that. So what we'll do is we'll distribute this, so it will be, we'll distribute this times this, and this times this, and then put all these together. So when I distribute it, I'll go ahead and put this line across here. I'll get a negative 2 times x squared will give you a negative 2x squared, and then this will turn into a plus 2. Then 2 negatives make a positive. This will turn into a plus 4x squared. And this will all be divided by x squared minus 2 squared. Okay, so what that gets you to, now you've got 4x squared minus 2x squared. This will turn into a 2x squared plus 2 divided by the denominator, which would be x squared minus 1 squared. And that's going to be the first derivative. So I found the first derivative. Okay, now let's take a look at the next step. And the next step is you're going to need the second derivative, so just go ahead and use the first derivative to find the second derivative. So we'll move things up a little bit here. We'll go ahead and scoot the whole graph down. And we'll start with the second derivative right here. So I've got the first derivative there. So what I'll go, and this will be step number 2. So step number 2, you want to find now the second derivative, and you have to use the quotient rule again. So to find the second derivative, and again it's the quotient rule, so it's going to be the denominator, which is x squared minus 1 squared, times the derivative of the numerator, and the derivative of the numerator would be 4x, then minus the original numerator, which is 2x squared plus 2, times the derivative of the denominator, but I'm going to switch to brackets here because this is going to involve the chain rule. You've got a composite function. So what this would be, is going to be, just looking at the denominator here, it's the derivative of the outer part times the derivative of the inner part. So this would be 2 times this thing to the first power. Go ahead and rewrite the inner part. Then finally times the derivative of what's on the inside, which would be 2x. So that's the derivative of the denominator using the quotient rule. Then we'll go ahead and put a line across this whole thing. And this is all divided by the denominator squared. So I'll have x squared minus 1. Now it was squared. When you square a square, now you've got it to the 4th power. So what this will turn out to be is this. Now at this point, it's tempting to do this. Go ahead and expand this thing, use the FOIL method, spread this out, distribute. And the trouble is it gets you into a lot of algebra if you do that. So I'm going to show you a little algebra trick here that will make this whole thing a whole lot easier. And it's based on this. Here is an x squared minus 1 right here. Here is an x squared minus 1 right here. So both these two terms have an x squared minus 1, so I can factor out an x squared minus 1, which I'll do, and I think I'll leave it in red here. I'm going to go ahead and factor out an x squared minus 1 out of this expression. Now, what that's going to leave me with will be this. So that here is an x squared minus 1 squared. I factored out this one, and I factored out this one. So I brought those out. Now, what's left over? I had an x squared minus 1 squared. I took one of them out, so I've got one of these left over. So I'll still have an x squared minus 1 right here, times 4x, then minus, you still got this term, so 2x squared plus 2. Now what's left over in this term is this, is you factored this out, so you still got 2 times 2, which would turn into a 4x. And then put a line across the whole thing, and that's all divided by x squared minus 1 to the 4th power. But now here's the reason for doing that. So you factored this thing out. Now the whole reason for doing this is when you factored it out of here, when you factor this thing out of here, is you've got, here's an x squared minus 1, and here's an x squared minus 1. So 1 on the top will cancel out 1 on the bottom, and you'll still have 3 left over on the bottom. So I'll cancel it out. This one on the top will cancel out 1 of these on the bottom. You've still got 3 of them left over on the bottom. And all that's going to do is just make the algebra a little bit easier to work with. So let's do this. Now, with what's left over, I'll go ahead and distribute this. So this times this and this times this. Multiply these two together, and you get a 4x cubed. Then you've got minus 4x. Then go ahead and distribute this thing. And when you do this, you'll have a minus 8x cubed. And then finally distribute this. This will become 8x and a negative. It'll turn into a negative 8x. The whole thing divided by, and now it's divided by x squared minus 1 cubed. Okay, now these you can put together and do the following. So what I'll do, I've got a 4x cubed minus an 8x cubed would give me a negative 4x cubed. And negative 4, negative 8 would give me a negative 12x, all divided by x squared minus 1 cubed. And that is going to be the second derivative. So I've got the second derivative of x. And I think I'll go ahead and put a little box around that just to kind of isolate it here. So I have found the second derivative. Okay, now we'll go to the next step. And I think I'll move this back up to the top first of all, just to show where it comes from. So on the next step in this process, we've now found the second derivative. Now to find the inflection points, they occur where the second derivative is equal to 0 or where it's undefined. Now let's discuss part B just for a second. Where the original function is undefined, the second derivative is undefined. So wherever you have an asymptote, you can think of that as being an inflection point. Strictly speaking, it's not, but it'll behave as an inflection point. So all we have to do now is this, is set the second derivative equal to 0 and solve for x to see if there are any additional inflection points. So we'll go back to our graph and we'll go down to where we were, and we'll go on to this next step. So what the next step says to do, to find any additional inflection points, take the second derivative and set it equal to 0. So what I'll do is take the second derivative, 4x cubed minus 12x divided by x squared minus 1 cubed, and set it equal to 0. Now, just from your work on fractions, the only way a fraction can be equal to 0 is if the numerator is equal to 0. So you can forget about the denominator and just set the numerator equal to 0. So I've got 4x cubed minus 12x is equal to 0. So again, the only way a fraction can be equal to 0 is if the numerator is equal to 0. And this should have an x right here. Okay, now I need to factor that thing and solve it. So out of this, I can go ahead and factor out a negative 4x out of both these. So I'll factor a negative 4x out. And what that leaves me with is an x squared plus 3, and set that equal to 0. Now, to find out where each of these equal to 0, set each factor equal to 0 and solve for x. So set that one equal to 0 and that one equal to 0. This one gives you x is equal to 0. So there is an inflection point. Then set this one equal to 0. So x squared plus 3 is equal to 0. And what that gives you is x squared is equal to a negative 3. Now, no number squared is equal to a negative, so what this means is it is never true. So that is never true. And what that means is there are no more inflection points. So you have no more IPs. So the only inflection point you found was that x is equal to 0. So now, just like we've done before, let's go back up to the graph and put that on the graph and see what it's going to look like on the graph. So we'll go back up to our number line. And what I've got here is this. And I think I'll do it in red again. Okay, that means that right here at 0, so when x is equal to 0, I've got an inflection point right there. So I've got an inflection point. Okay, now let's take a look at our steps again. We only found one additional inflection point. So let's go back to the steps. So now that we've identified the inflection points, we want to use the inflection points and the asymptotes to divide the graph up into separate intervals. So let's do that. Now what the intervals will look like, I'm going to do it in black. I'll have an interval right here at this inflection point. It'll go down like this, straight through here. And the intervals will actually be this. I'll have one interval that goes from here to here. Got another interval that goes from the asymptote to the inflection point. Another interval from the inflection point to the asymptote. And finally a fourth interval from the asymptote out to a positive infinity. And this one, of course, is going to be a negative infinity over here. So now, just like before, we want to pick a test point inside each of those intervals. So let's look at our rules. So what the rules say, number 5, pick a convenient test point inside each interval and evaluate the second derivative to see if it's positive or negative. And that'll tell you whether the function's concave up or concave down. So let's do that. Now for my test points, again, I'm going to pick something convenient. If I can, I'll pick an integer. So in this interval right here, I'm going to pick -2. That'll be my test point. Now I'd like to pick an integer, but in this one I can't, so I'm going to pick something convenient, and the most convenient point I think would be about a -0.5. Same problem here, I can't pick an integer, so I'll pick a positive 0.5. And then in this interval, I can pick an integer, so I'll pick 2. So I'm going to evaluate the second derivative at -2, -0.5, 0.5, and 2. So we'll go way back down where we were before, and we'll finish this part up. So this is going to be step number 5. We'll put it right in here. So step number 5 says evaluate the second derivative at -2. That's the first test point. Evaluate the second derivative at -0.5. Evaluate the second derivative at positive 0.5, and finally evaluate the second derivative at 2. And all you're curious about here is, are they positive or negative? So what the second derivative is, it's going to be this function right here, 4x cubed minus 12x divided by this. So just everywhere you've got an x, plug in a -2. So this first one would look like this. I'll have -4, and in place of the x cubed, put a -2 cubed minus 12 times a -2 divided by a -2 squared minus 1, and the whole thing cubed. Now, if you stick that on a calculator, what will happen is it'll turn out to be a positive number in the top. It will turn out to be a positive number on the bottom. So a positive divided by a positive gives you a positive. And again, you're not concerned about the actual numerical value. If you need to, just go ahead and take this, put it on a calculator, and it'll give you an answer. But that's going to be concave up. So I know the graph is going to be concave up, and that's going to be in the interval from negative infinity to the first asymptote, which would be at a -1. So if we looked at our graph up here, it tells you that it's going to be concave up in this interval right here. Now let's figure out what's going on in this interval right here. So we'll go back down again. And we'll go ahead and finish up these other three here. So this one would be -4 and plug in a -0.5 cubed minus 12 times a -0.5 divided by -0.5 squared minus 1 cubed. And again, what this one's going to give you, then you'll have a positive in the top divided by a negative in the bottom, which will give you a negative, which tells you that it's concave down in this interval. Concave down. So it's going to be concave down in the interval from -1 to 0. Now go ahead and plug in the positive 0.5. So it's the same process. So 4 times a 0.5 cubed minus 12 times a 0.5 divided by 0.5 squared minus 1, the whole thing cubed. When you do this one, it will turn out to be a negative divided by a negative, which turns into a positive, which again tells you that it's concave up. So this is going to be concave up in this interval. So in the interval from 0 to 1. And then finally in the last interval, plug in a 2. So -4 divided by 2 cubed minus 12 times 2 divided by 2 squared minus 1, the whole thing cubed. And when you put this on your calculator, you'll come out with a negative divided by a positive, which gives you a negative, which tells you that it's concave down. So it's going to be concave down in this last interval. Concave down. In the interval from 1 all the way out to a positive infinity. Okay, now strictly speaking, this is the answer to your question right now. You wanted to identify the intervals where it's concave up and concave down, and you have done that, so the problem is actually finished. But just like we've done on those previous ones, let's go up and take a quick look at the graph and see why it all makes sense. So I'll go from here, let's go back up to our original graph. Now remember, it's concave up, concave down, concave up, and concave down. So on the original graph, what we've got is, it is concave up in the first interval, it's concave down in the second interval, it's concave up in the third interval, and finally it's concave down in this last interval. So what that's going to look like, if you put it all together, would be the following. It has to do this. The graph, if you actually did it on a calculator, would look something like this, and we'll put the little hairs on like we've done the previous ones. So first of all, it's concave up in this interval, and it approaches an asymptote. So it'll come in like this and approach the asymptote, and goes up like this, and it goes off like this. Now again, if you use those little hairs that we learned last time, it's concave up in this interval. So we'll use the little hairs to indicate concave up. Then in the next interval, it's concave down, and it hits an inflection point here at 0. So what that's going to be, if it's concave down, it will come from the asymptote, something like this, goes over kind of like this, and it goes like. So this will be off to infinity here. Now again, I'm going to go ahead and put the little hairs on there. So it's going to be concave down in this interval. So it's increasing but concave down. when it gets to this inflection point, it switches to concave up. So on this side, it's going to do this. It's going to approach this asymptote over here. Now again, we'll put the little hairs to indicate the concavity. So it switches to concave up in this interval. And then finally, in the last interval, it's concave down again. So the graph, if you actually sketch the graph, it comes from the asymptote and looks something like this. And again, we'll put the little hairs to indicate concavity. So it's concave down in this interval. So really, the only difference between this and the previous problem we did, anytime you've got asymptotes, a rational function with asymptotes, nothing, I'll put a little box around it, is the only thing you have to add this additional step at the very beginning. So the first step at the very beginning is to go ahead and find the asymptotes, this one and this one. And then the asymptotes can behave as if they're inflection points because the concavity might change at an asymptote. Then go ahead and follow the 6 rules. Now, if you go through the rules, after you found the asymptote, run through these 6 rules, and it will allow you to identify any additional inflection points. Then that will tell you what's going on in each interval. Again, if it's concave up or concave down, you can tell it, and then the final answer will look like, and we'll go all the way back down here at the bottom again. This part right here, you identify the intervals where it's concave up or concave down. So that's an example of a problem that has asymptotes, and it takes a little more work on the algebra just because you've got the quotient rule in it. But other than that, the process is very similar.